Hello all, welcome back to our channel. Today, we'll be learning about MAC addresses. A MAC or Media Access Control is a unique identifier for network devices. MAC addresses can be represented in various ways depending on the system or vendor. For instance, Linux and Apple devices would typically display a MAC address as 6 groups of 2 hexadecimal digits, separated by colons. In contrast, a Windows system represents the MAC address with hyphens instead of colons. Meanwhile, Cisco devices displays MAC addresses with periods separating 4 sets of hexadecimal digits. The manufacturer typically hardcodes the MAC address into a network interface card, or NIC. NICs are the hardware components that enable devices to connect to a network, which is built into your device. The first 3 pairs of a MAC address are known as the Organizationally Unique Identifier, or OUI. This identifier can help determine the manufacturer of a particular piece of network hardware. For instance, if the first 3 sets of a MAC address are 00:0D:93, this would suggest that Apple manufactured the network interface card, as this OUI is registered under their name. Both MAC addresses and IP addresses are used to identify devices on a network. But they do it in different ways. A MAC address is a physical address used for communication between devices on the same local network. On the other hand, an IP address can change and is used to identify devices on the internet or a larger network. So, a MAC address identifies a device locally, while an IP address identifies a device globally. Let's understand this with a simple example. We have a router which is the connecting point between 2 separate networks. Each network hosts 2 computers. On the first network, we have computers A and B, while the second network hosts computers C and D. Suppose computer B wishes to send some data to computer D. The first thing it will do is determine whether computer D is located within the same network. Upon discovering that computer D resides on a different network, computer B recognizes that it needs to forward the data to the router so that it can be sent across to the other network. Now, the transmission of data within a network is usually facilitated through MAC addresses. However, in this case, computer B only knows the router's IP address, which is typically configured as its default gateway. So, to find out the router's MAC address, computer B will broadcast an ARP or Address Resolution Protocol request to all devices within its network. In essence, this ARP request is asking, who owns this IP address? The device owning the IP address, which in this case is the router, will then respond with its MAC address. Once computer B gets the router's MAC address, it places its own MAC address as the source MAC address, and the router's MAC address as the destination MAC address and sends the data to the router along with the IP address of computer D. Once the router receives the data from computer B, it will check if the IP address 192.168.1.3 is in its network. If this IP address is in the network, the router broadcasts the ARP request asking for MAC address of the device with that IP address. As the IP address belongs to computer D, it would respond with its MAC address. Once the router receives the MAC address, it's ready for data transmission. The router replaces the source MAC address in the data packet with its own MAC address, and the destination MAC address with computer D's MAC address, and forwards the data along with computer D's IP address. In this example, we saw that the MAC addresses used in data transmission would change, but the IP address remained the same throughout the transmission. In this way, the data sent initially from computer B successfully reaches computer D, which is on a different network. Let's consider another scenario where a computer in your home wants to connect to a server on the internet. The computer doesn't know the server's MAC address because they are not on the same local network. What it does know, however, is the server's IP address because IP addresses are used for device identification on the internet. When the computer sends out its request to connect to the server, it doesn't send the request directly to the server. Instead, it sends the request to its default gateway, which is typically your home router. To do this, the computer needs to know the router's MAC address. If it doesn't already know it, it uses the ARP process we discussed earlier to find it out. It then sends its request, which contains the server's IP address along with its own MAC address and the router's MAC address. When the router receives the request, it looks at the destination IP address and realizes that this IP address is outside the local network. It then sends the request to the ISPs along with their respective MAC addresses. The process continues this way, with the request being forwarded from one network to the next until it finally reaches the server. Each network along the way is like a step in a journey, and at each step, the device sending the request onto the next network uses the MAC address of the next device in line to ensure that the request gets to where it needs to go. In contrast, the IP address of the server remains the same throughout this journey. That's how MAC addresses are used with IP addresses to connect devices over the internet. We can view the MAC address of a Windows device by typing ipconfig/all on the Windows command prompt. On Linux and Mac devices, you can fetch the MAC address by typing ifconfig on the terminal. And that wraps up our deep dive into the world of MAC addresses. I hope you found this video informative and that it has helped clarify how these unique identifiers function within and across networks. If you enjoyed this video and learned something new, please hit the like button, share it, and subscribe to our channel for more content. If you have any questions or topics you'd like to see covered in future videos, feel free to leave a comment below. Thank you for watching. Until next time, stay curious and happy exploring.